good here.
Okay.
Calling in good work, guys.
Oh, this guy's
There you
testing. Yeah, can you hear me?
It's going to be a 2-second delay, Bruce. You're going to have to wait through the camera.
Whoa. Can you hear me? I'm speaking to there, right?
Yeah, you're actually speaking right here.
Oh, yeah, right here, right. We're not getting anything back.
This is Newport.
Yeah, hit unmute and tell them real quick that we're working on it.
Oh.
Okay, in Newport, I can hear you over the
Camera?
site. Can you hear me?
Yeah.
Yes, we can hear you. There may be a delay.
Explain.
Is there a delay?
Yes, there is. Let me time it. Starting now. Go.
Okay, so this is a test. Stop. What did he say?
9 seconds.
9 seconds? Okay, we're going to have to work on that. Wow.
Buffering in the internet, you know?
Oh, God.
Yeah.
Okay, all right. So we just leave that like it is, right?
Yeah.
Okay.
Yeah.
Okay, so let's look at problem set 1, right? I revised these a little bit. I don't know if Gene has uploaded them to Sakai yet. Okay, right. And that's, to be, honest with you, I think this is what's going to happen for every problem set. So the problem set solutions that are posted on Sakai, I think they're all going to be revised. So just be aware of that, okay? And before we get started, I want to point something out. Oh, here's the, Gene may want to, we'll send you instructions on the telephone conferencing. This is central number at NPS, so we're handling that. This is done just through NPS for questions, okay? And we'll send out this information in an email message and also put it on Sakai. Now, regarding Sakai, I made a mistake yesterday. We're not going to be using resources, okay? This is what I've used in the past. But Gene says no, and he knows best. So I don't, and in fact, you don't even see this. You don't see it. I just found out yesterday. I need to use student view a little more, okay? So here's the way we're going to do this. I'll be posting a quiz today, this morning or this afternoon, and it'll be in assignments. So I'll set up an assignment. Maybe some of you are familiar with this. I'll set up an assignment. There'll be a start date and an end date. Oh, gosh. Anyway, the quizzes will be posted in there. You'll find the quizzes there. Okay, and you will upload. Yeah, so when you, not except for the on-site students. The on-site students will just submit a hard copy to me. Right? That goes for homework and quizzes and lab reports. All submissions. On-site students will give it to me. You can, just before or after class, or go to my office. If my door is closed, you can slide it under the door, whatever you're wanting to submit, okay? But for the distance learning students, you will upload after you do a quiz, you'll upload it into the assignments. You've probably done this, they've probably done this before, okay? And then I will grade them and I will put them in there and you can download them. The students here, you'll come to my office and there'll be a folder where you can look at your quizzes. I don't release the quizzes, okay, but you can look at them as long as you want to. Okay? All right. So, I'm hesitant to say this, but are there any questions? Quick, you guys got 9 seconds. Before we... Do we have any quick questions here? Okay, any distance learning questions? Should be so far. We're going to work on this 9-second delay. I don't know if there's anything we can do about it.
I think it's, we just have to acknowledge the fact that there's a 9-second delay and work around it.
Gosh.
We're streaming high definition video over the internet to the East Coast. There's buffering and so forth.
The VTC here, it's less than 9 seconds.
And they're running 400.
But that's because...
Yeah.
Okay. All right. Well, we'll see. Maybe there's something.
It's just an inconvenience. I mean, we can make it work.
Yeah, okay. All right. So let's look at, this is problem set 1. Okay. Now, we're not really into acoustics yet. Some of these problems they're really just exercises. A few of them are interesting, I think. But, so let's just do them. And here's, the first one is 2.1. So what this is an alternative approach to what we did in lecture. And this is in regard to the bulk modulus for an ideal gas. So it's really just an exercise just to kind of get you used to what's going on with this is the thermodynamics here. Okay, so we begin with, we're instructed to begin with this equation, 5.2.3, and you'll recognize this as equivalent to PV to the gamma is equal to, is a constant. So this is an adiabatic process in thermodynamics, as we discussed. And for fluid dynamics and acoustics, the volume's no good. We got to go local. We go to the density. So it's expressed like this. This is called an adiabat. I think I might have mentioned the word in the past. An adiabat denotes the fact that this is a curve in the pressure versus density plane, like an isotherm. You've all heard of an isotherm. An isotherm denotes a curve in some, pressure in thermodynamics, pressure volume plane, typically. Yeah, I guess would be it. So this is what people use for the curve for an adiabatic process, as opposed to isothermal. So we're instructed to express this in terms of the condensation. Remember, here's the condensation. It's the fractional change in density, the change in density divided by the equilibrium density. So we can invert this and we get this for the density in terms of the condensation. We substitute it into the adiabatic expression here, and we get this. And now we're instructed to go ahead and make I think we did this differently in lecture in several ways. But we're going to go ahead and make the small condensation approximation here. This is what we do in acoustics. It's almost always true in acoustics, even for nonlinear acoustics. But especially for linear acoustics, we want very small condensations. We're just looking at, as I've said many times, acoustic wave for us is just a perturbation from the equilibrium state. And the reason we do this is a nonlinear relationship here. Okay, P is not proportional to S. We're going to go to the difference in pressure here. This is not a linear relationship, but when we make the small condensation approximation, it becomes a linear relationship. This is greatly to our advantage. If we did not do this and other approximations, we would not have the standard wave equation. We would have something a lot more complicated. And as I've told you, if you're interested in that, that's part of pH 4459 nonlinear oscillations and waves. We plug it because we have to make sure we populate the course so that it's offered, okay? And incidentally, there are no tests. Did I tell you guys this? I don't think I did. Steve has taken it, right? You took it last spring. There's no testing. It's just homework. I used to have, in that course, Savas?
Yeah.
Did you take it too?
Yes.
Oh, did you take it with Steve?
Yes.
Oh, okay. Yeah, good.
It's a great course.
Thanks. Yeah, it's a good course. Professor Loraz and I are, we were graduate students together and at UCLA, and we're the nonlinear generation. The nonlinearity became really hot in the 70s and 80s with chaos and solitons and all kinds of other nonlinear behavior. It just became really hot. So there's a ton of people got their PhDs in nonlinear science, okay? So, okay, anyway. Okay, fine, that's good. Now, what we're interested in here is the acoustic pressure, the pressure difference. So we'll write it, we can express this like this, easy algebra going from here to here. Okay, I don't know why I didn't call it lowercase p, but I'm just leaving it like that. Now, we also found, if you look back in the lecture notes or in the book, when we just do a Taylor expansion of the pressure with respect to the density for adiabatic changes, we get this. This is the first order Taylor expansion, where this is the adiabatic bulk modulus. Okay? So here, this is necessarily linear because we truncated the higher order terms. And now if you compare these two, for these two to be equal, you can see that we can identify what the bulk modulus, adiabatic bulk modulus is for an ideal gas, and it's equal to gamma p naught, which we derive differently in lecture. So that's part of the point here, okay? There's more to this. Let's see. So this is in terms of the equilibrium pressure. We can also put it in terms of the temperature. We can use the ideal gas law. Excuse me. Now this doesn't look like the standard ideal gas law. PV is equal to nRT. But as we discussed, it's equivalent to the ideal gas law. You can go back and look at this. This R is the specific gas constant, the universal gas constant divided by the molar mass. So we can substitute this expression for, we can evaluate, this is true off equilibrium too, but we apply it in equilibrium. We have equilibrium pressure P naught, density rho naught, and we're going to use Tk, T sub k here to denote the equilibrium temperature now. So we substitute that in there and we find this formula for the adiabatic bulk modulus of an ideal gas. And you can see here that for constant density, the density is not, you're not changing the density, it's proportional to the temperature. So what this means, the bulk modulus is the stiffness. Remember, it's how the pressure changes with density. It's easier to think of the reciprocal, which is the compressibility. That's how the density changes with pressure. You pressurize something, the density is going to change, right? So, which is 1 over this. So you can see that the stiffness, the bulk modulus is the stiffness here. It plays the role of the stiffness for the sound waves. So if you double the absolute temperature, you double the stiffness, and the speed of sound goes up how? Does it double? Square root of 2, right? Square root in there, okay. All right, any questions about this problem? Yeah.
Just a general question. It said like linearize this equation or whatever.
Yeah, this is now linearized.
So that's all that means is just by some approximation or a Taylor series or something, get it to a linear.
Small deviations, right. It's a big deal, you know, in all waves. It's just very standard. And often you can get away with that. In acoustics, it's often extremely good approximation. But if you start cranking up the amplitude, you're going to start to see non-linear effects that just have no linear counterpart, weird things. And we'll talk about one of those. I've mentioned it, and we'll talk about it in another problem. Those are shock waves. We'll actually talk a little bit about shock waves today, which you've all heard of. Okay, any other questions? So next one is 4.2. Oh, this is, okay. Now, in fluid dynamics, when people talk about incompressible flow, I don't have time to write this down. When people talk about incompressible flow, what they universally mean is that the density is constant everywhere in space and time, okay? It's absolutely, the density is constant. Now, in reality, you know, every fluid has some compressibility, so it's not going to be true. This is not going to be exactly true, okay? But often in fluid dynamics, it's a very good approximation. And as I've told you, it greatly simplifies the analysis. Fluid dynamics, this is the first thing they look for, usually. When they're dealing with some kind of fluid, they first want to know, is it approximately incompressible flow or not, okay? There's a more general approach that I had never heard of until I saw this problem about 10 years ago. So we're going to look at this from a more general point of view. We're going to define incompressibility here to be if you here's our coordinate system. If you look at a fluid particle here, right, that's moving, in general has some velocity, we're going to demand that the density of the fluid particle doesn't change. So that's a definition of incompressibility, and it's actually more general than this. The density is the same everywhere, okay? Here's another fluid particle, right? Over here, some other velocity. Its density does not necessarily have to be the same as that, according to this KFCS's definition of incompressibility. So this is a more general situation. To be honest with you, I don't know if it happens in practice. I'm suspicious that it doesn't, but that's okay. We're just going to assume this, okay? We're going to look at the more general definition. So the density is not necessarily constant here. It's only constant if you follow with this particle, and you've got to follow the particle. So how do we express that mathematically? Well, we got to use this so-called convective derivative that we derived in lecture. To follow the particle, if you want to see how something is changing in time when you follow the particle, you don't just do this partial time derivative. There's also the fact that the particle has moved in space. You have to follow the particle. That's what this is doing right here, as we derived in class. So we're going to set that equal to 0 for this general definition of incompressible flow. All right. So, fine. What else do we know? Well, we know that no matter what, mass has to be conserved. For any non-relativistic flow, you've got to have conservation of mass. So we've seen that the general statement of conservation of mass is called the equation of continuity, and it looks like it's this right here. We can expand this. The divergence of a scalar function times a vector function is just what you'd guess. It's the scalar times the divergence of the vector plus the vector dotted with the gradient of the, so it's vector identity, okay? It's a product rule. This is a product rule for vector differential operations, okay? So if you have trouble with this, you can look it up. I'm sure there'll be there must be in the back of our book in an appendix.
Yeah.
Okay, thank you. So we know that has to be true. We know that this has to be 0. Now, if you look at these two expressions here, what do you see? They both have the time derivative. This term is common here, and this has to be equal to 0. So this is going to have to be 0 by our incompressible assumption right here. So this, I'm not doing this right. Excuse me. This and this have to add to 0 from this equation right here. So we're left with the fact that this has to be 0, and rho's not 0, so we conclude that the divergence of u has to be 0 for an incompressible flow. Now, I can't leave it at this. I have to tell you how everyone else in the world looks at this, okay? Here's the way everyone else in the world looks at it. I've never seen this before, okay? When people talk about an incompressible flow, as I told you, they mean the density is constant everywhere, okay? So in that case, what they do is they look at the equation of continuity. Because the density is constant, there's no time derivative. The density being constant here, rho naught, comes outside here, and you immediately conclude that the flow is divergenceless. That divergence of u has to be 0. So this is how everyone else looks at it. But it is kind of interesting that there is this more general perspective here, although I don't know if it occurs in practice, in real systems. There's another part to this problem. What's the speed of sound for an incompressible fluid? Remember, the speed of sound is how the pressure changes with density. It's a square root. You got to do this adiabatically, because that's what acoustics is, almost always. And you evaluate it in equilibrium. Well, we don't have any density changes here for a strictly incompressible flow. So this is 0, but we can have pressure changes. So the speed of sound is infinite. Now, in a real fluid, like I said, there's always some compressibility. So the speed of sound will be finite, but it will be large. It will be large. Okay, any questions about that problem? Whoa. Okay, the next one guess I don't need this. Yeah, I don't think I need this. Okay, the next one is 5.2. Okay, so we derived the standard wave equation yesterday, and then we discussed it for the pressure, for the acoustic pressure, which is the deviation of the pressure from the equilibrium value. And then we went through and showed that all the other acoustic variables also satisfy the wave equation. We didn't quite do the whole derivation for the particle velocity, but it's in the notes. And we're going to look at it from a different perspective here. We're going to show that the acoustic particle velocity, a quantity we call u, obeys the wave equation. So following what's stated in the problem here, we first of all write down our basic equation here. Here's the thermodynamics equation. And again, like I told you yesterday, we're going to be using the bulk modulus less and less here. We as a parameter of a fluid, we want to use the speed of sound. It's much more direct. So we'll use this expression here, not this one. These are equivalent, but we'll use this. Here's the linearized equation that expresses conservation of mass. Here's Newton's second law, Euler's equation, also linearized. And now we want to go to see, we want to get one equation in U, not the pressure P like we did yesterday. We want to do it, get the equation for U, the particle velocity. So first thing to do is, P and S are very simply related. Let's get rid of S here. So that's what I've done right here. And I've solved for the divergence of U. We've substituted one to get rid of S here in terms of P. And now we have two equations and two unknowns, the U and the pressure. You can also think of it as four equations and four unknowns. You know, think of U as a vector or as three components. Okay, so how do I eliminate the pressure from here? We've gotten rid of the, here, from these two equations, how do I eliminate the pressure? Well, you can see that this involves the gradient of the pressure, this involves the time derivative. So I want to take the time derivative of this equation and the gradient of this equation, and then add or subtract the two to eliminate the pressure. And that's what I've written right here. I've moved things around a little bit. I'm taking the gradient of this equation right here. Okay, and that's how I get this. I've also multiplied through by c squared, and you'll see why in a moment. Does that mean we just lost, it's not red anymore.
It's been green most of the time.
Oh, I heard a sound.
Is it unmuted?
Yeah, I think so.
That's probably one.
Yeah.
Oh, we're supposed to mute this.
Yeah.
Oh.
Hit the mute button. There you go.
Oh, that means there may be problems with the audio. Okay. I forgot about that. It's complicated. Yeah. This is all right. So we take the gradient of this equation, all right, and I also multiply through by c squared. And then we look at this equation, and we're going to take the time derivative, right? And you'll notice what I've done here. When I take the time derivative here, I can slide it right through the gradient. They're independent operations. They commute. Those two operators commute, as we've discussed. And now I've got these two equations, and now I just subtract the left-hand sides and the right-hand sides. So if this is true and this is true, the difference is going to be true. So I do that because I cancel these terms. That's why I multiply through by c squared to clean this up. So when I take the difference here, I get 0. And now we get this equation, which does not look like the wave equation, does it? It's not a Laplacian here. Okay, but that's the first part of the problem here. The next part is to recognize that there's a vector identity for any vector function. The Laplacian on a vector obeys this well-known identity. This is used all the time in fluid dynamics, electricity and magnetism, electromagnetic theory. So I don't know if you guys have seen this before, but this is a standard identity. And in our case, in acoustics, the velocity has no curl, as we derived yesterday. I think it was yesterday. So long ago, I can't remember. I think it was yesterday. Okay, we derived that. So we can replace this gradient of the divergence with the Laplacian, and now we end up with the wave equation, the standard wave equation. So yesterday we did this. We didn't quite do it all of it, but another approach to this is through the vector potential, whose gradient equals the velocity, analogous to electromagnetism. And you can also show from that root, that the particle velocity satisfies the wave equation. Yes?
What does it mean when it says U is rational? What should we understand?
See.
Irrotational.
Oh, irrotational?
No
Yeah, no curl. Yeah. So the curl of a vector field measures the vorticity. This all comes from fluid dynamics, as I told you yesterday. So the word irrotational and rotational refers to the curl. Okay, any other questions? Guess we should wait 9 seconds? I don't know. Well, they can speak. You know, if they chime in, we'll stop.
Well, yeah, we'll have to figure out a way to get them addressed.
Okay, so next one is 6.1. Okay, find the speed of sound in hydrogen at 1 atmosphere and 0 degrees Celsius from its values of the equilibrium pressure, equilibrium density, and ratio specific heats at the temperature and pressure. Okay, so the formula here for the speed of sound, this is what we almost always normally use. And if you, actually what I suspect people use a little bit more often is this, okay? But they're equivalent with a unit, with a molar mass, as we've discussed. They're equivalent. This is what we normally use. But if you look back at the derivation, or if you use the ideal gas law, you can see that this can be written like this. Okay, this is when we derived it. This is actually what we derived, and we commented that you can use the ideal gas law to express it like that. In this problem, this is unusual. We're going to use this form. Okay, because that's the quantities that we look up in the back of from an appendix. So here's the for hydrogen at 1 atmospheric pressure and 0 degrees Celsius. Here, incidentally, 1 atmosphere is about 1 times 10 to the 5th Pascal. We'll be using this a lot. To 3 figures, it's 1.01. So most people just call it 1 times 10 to the 5th. Don't worry about this. And that's fine. 2 significant figures is fine for our problem. For almost all of our problems, it'll be fine. So when we need more precision, then you're a little more careful, right? So in that case, you may want to include this 1% effect here. But there's a 1 right there. The ratio of specific heats is 1.41. So we just plug these values in, and you punch it in your calculator, and you get 1260. Meters per second. And I've written this to, speaking of significant figures, right. Okay, I take it all back. In this problem you'll want to notice something here. We're doing everything to 3 significant figures. I am going to use the 1.01, okay, sorry, take back what I said. We want to do this to 3 significant figures. Now our result is then this. This is actually not the correct way of stating the result, is it? Because if I look at this, somebody else looks at this, they don't know whether this 0 is significant or not. So how should we really express this? Although people usually don't do this. We really should write it like this, shouldn't we? Because now you see it's implicit here. You can see it, or explicit. You can see that there's 3 significant figures. But here you wouldn't really know, okay? So anyway, this is We have three digits, three figures of accuracy here, of precision, okay? Now, if you look this up in the tables in the back of the book, which you're going to be doing a lot this quarter, okay? You'll get used to going to back there and looking up different quantities, not just the speed of sound, but other quantities. It states this. So these aren't the same. This is about 1270. This is 1260. So I see a difference here of 10 parts out of 1270, and that's about 0.8%. So we have a 0.8% discrepancy here. Is there something wrong? You know, this is so here's what you have to be careful of. And this can happen in this book, and it can happen elsewhere when you're doing acoustics, especially. You calculate, this is a theoretical value, you get this value. This value, I don't know, this could be an experimental value. You know, this is just from our model. You know, we've made approximations here. You've seen the linear approximations, right? So, and there are actually other approximations that we'll eventually discuss that even exist on the linear level. Attenuation, sound. So we'll talk about that later in the course. So you may wonder what the problem here is. However, if you think about it, three significant figures here roughly means 1%. Roughly, okay? So we only expect this to be valid to 1%, and we're seeing a 0.8% error, so there's no reason to get excited here, okay, and think that there's something going on. These two things are equal within the precision of our calculation. Finally, here's in this problem. This is interesting, okay? You'll do this a lot in the laboratory here. It's a really important way to look at things when you're considering when you have a discrepancy, or you're thinking about a deviation of something. For here we have this discrepancy, right, between these two values. Suppose this were a measured value. This happens all the time in the lab. You measure this, you look it up, and you see that, and you think, okay, what's the error? What's causing that? Could it be temperature? The speed of sound in a gas depends upon the temperature, right? So could it be that we just didn't specify, this is at 0 degrees. Could it be that when we did this experiment, it wasn't exactly 0 degrees? Well, the way we address such issues is we look at the percentage error. So here I know that the square of the speed of sound is proportional to the temperature. So I know it's proportional to the absolute temperature. This means that c squared, I'm going to write this out once in length here, but we're going to be doing this a lot, even in this course, but especially in the lab. If I take a differential of this, okay, or a variation, I'm going to get, when I take a differential of this, I get that. Okay. I'm writing delta here. You can think of it as a d if you want. If you want to use a d, that's okay. Now what I do is I take this and put it underneath that. I divide. I take this divided by that and this divided by that. And you see what happens? We get 2 delta c over c is equal to delta. This is the way that especially experimentalists like to look at things. It tells me that if I want to know how, let's say that the effect of changing the speed of if the temperature changes, how does the speed of sound change? As long as the temperature doesn't change by much, I don't need to use an exact analysis. I'm just going to use this approximate analysis here, or differential analysis. So a 1% change in the absolute temperature corresponds to what kind of change in the speed of sound? 0.5%. You got to bring, yeah, it depends on which way you're going. Which way you're going here, okay? I think we did it the other way. Here. In this case, we have a change in the speed of sound of about 1%. That corresponds to a 2% change in the absolute temperature. What does that mean as far as the actual temperature change goes? Okay, well, you multiply through here. Remember, this is 273 degrees. It's 4.4 degrees Celsius. So if this were this is a theoretical value, but if it were an experimentally measured value, could the deviation here be due to temperature? No, that's huge. 4 degrees, that's huge. So unless you have a really crude thermometer, okay? If we did get this discrepancy, then we'd have to look for something else. And the way we know, that temperature is not responsible for the deviation here, if this were a measured value, is from this simple analysis right here. So we'll do more of that in the laboratory. And like I said, it'll occasionally come up in lecture and problem sets too. Okay, any questions about that one? That's 6.1. How many more do we have here? 2 more? Oh, we're fine, right? Yeah, I think we're going to be fine. Okay. So, 6.3. Okay, for a perfect gas, means an ideal gas, does C vary with the equilibrium pressure? I don't think anybody can answer this question. Right? This is or some you can think this is what we sometimes call a loaded question. If I take a gas in a cylinder and I compress the gas in there, does the speed of sound change? Anyone? Do you know? No, you have to specify what you're holding constant when you do this. Is it constant temperature? Are you compressing it adiabatically? It's going to make a difference. So I think what they intend here is when they say, does it vary with equilibrium pressure? I think they probably mean the temperature is being held constant, but we really don't know, okay? This is a correct statement. This is the speed of sound. It depends upon the temperature. It's, if you change the pressure, the equilibrium pressure, but don't change the temperature, the speed of sound stays the same. That's the correct statement.
This is for the gas, but for the liquid should be pressure and the temperature.
Yeah, for a liquid, forget it. It'll depend upon both the pressure and the temperature. As far as I know, it's always true. It's definitely true in water. Now, there's another question here. Does the speed of sound vary with instantaneous pressure in an acoustic wave? So let's imagine we have a simple mono-frequency wave. If we look in space, let's look in space here. Okay, so we have this. We're going to take this to be a traveling wave of definite frequency. And here's what the acoustic pressure looks something like this. Okay? Now, at this moment right here, at this point in space, and this is at some fixed time right here, this is a compression, right? So what's the temperature at in this location? It's going to be a little greater than the equilibrium temperature. What about over here? It's a little less. It's a little colder. That's right. So what does that mean? For the gas right here, this local speed of sound is a little bit greater than the equilibrium value. So what effect do you think that's going to have on the waveform here? This crest is going to move. We call this a zero crossing because that's what it is. Okay? Here, there's no change in temperature. So this point is going to be moving at our speed of sound, our linear speed of sound. What about a point here? Because it's going to be moving at a greater speed. It's going to be moving at c plus some quantity. What about down here? It's colder, so it's going to be moving, and by it's a symmetric situation, it's going to be moving a little less. Now, in linear Okay? So, in linear acoustics, however, this is very small. This is going to be negligible. So we don't have to worry about it. But once you start to crank up the amplitude, you can see this effect. And in fact, we have a demonstration of it that we show. And what happens is, if you follow this wave, the fact that the crest is moving a little bit faster than the zero crossing, and the trough here is moving a little less than the zero crossing speed, means it's going to distort. The wave will start to distort. Look something like this. Okay? Because if you follow it along here, this point's moving, it's coming closer, and this one's moving back. And eventually, they're all on top of each other, and we have a name for that. What is it? Shock wave. That's a shock wave. This is one of the ways. A shock wave in sound occurs due to two reasons. This is one of them, that there's a temperature effect. And you can see physically why it can come about. If we don't have a small amplitude here, the wave's going to distort. And it's going to distort into a series of shocks traveling here. Okay. So what problem are we working on here? 6.3. Oh, here's another interesting problem. What is the isothermal speed of sound? Well, remember, the speed of sound is how the pressure changes with density, whichever kind of process you have. Usually it's adiabatic, almost always it's adiabatic for sound. But if you look back at that derivation, it really doesn't matter whether it's adiabatic or whatever it is. You just need to take the partial of the pressure with how the pressure changes with density for whatever is being held constant. It could be an adiabatic process, it could be an isothermal, or it could be some superposition of the two, actually. So to find the isothermal speed of sound, the square, we take the pressure changing with density. And here's our ideal gas law. For isothermal sound, we just hold T constant. And you can see that when we do that, we're just going to get this. And it's convenient here to connect this with the standard speed of sound, the adiabatic speed of sound. Remember, that's given by this, right? So I can come up with a simple relationship here. The isothermal speed of sound is the adiabatic speed of sound divided by the square root of gamma. That's how we get rid of this, and we get at the isothermal speed of sound. So this is useful because we all are familiar with this. For example, for air, it's 343 meters per second at room temperature. The ratio of specific heats is 1.4. So the isothermal speed of sound is less. It's significantly less. Look at that, 290 meters per second compared to 343. Most people don't have an appreciation. This is not usually relevant. What's relevant is the percentage difference, as we were just talking about before. The percentage difference between these two is about 15%. So it's a big effect. Why is the speed of sound, isothermal speed of sound, less than the adiabatic speed of sound? Why is that? Here, we have these compressions, and it's adiabatic. The temperature goes up. The fluid here, which is a gas, is going to be stiffer. It's going to be stiffer, as we discussed, right? And well, what we discussed was yesterday, when a medium is less stiff, the speed of sound goes down. So that's what we're seeing here. Speed of sound goes down. And this is measurable. You can reflect sound off some distant object and time it. This is not that hard to do, right? If you know the distance and you know the time, you can calculate the speed of sound. And I'm sure back in Newton's time, they could have done this to better than 15%. I don't know if anybody did it, but it's too bad. It'd be nice to prove Newton wrong, right? That'd be instantly famous. For 100 years, people have been trying to prove Einstein wrong, all the time. It's been going on for a century, right? And some of them are actually not crackpots. Some of them are serious. Most of them are crackpots. But there's been serious scientific work to question his theory of gravitation. That's called the theory of general relativity. There have been a number of competing theories. And so far, they've all fallen by the wayside. Einstein's has emerged as the correct theory. So, you know, people naturally want to prove somebody who's famous somebody wrong because you'd be instantly famous, right? You'd get, you know, a huge number of hits on YouTube, right? So that's what's popular these days, right? But anyway, I think this could have been measurable. 1700s, somebody could have measured this. So if anybody gets interested in this and finds out, I don't know the history, but if you find out, share it with us. Send it to me, you know, email it. And then I'll check it over, and then I'll send it out. If it looks valid, I'll send it out to the rest of the class. Okay? All right, any questions about this problem? Okay, there's one more. Now, unfortunately, we haven't discussed plane waves yet. All right? But it's not a big deal. Think of a string here. Think of the displacement of waves, transverse waves on a string under tension. You're familiar with this kind of representation for a plane traveling wave. This is a monofrequency traveling wave. Okay, and all that's important here is, I mean, sound satisfies the wave equation. So does waves on a string. So you know we're going to have a solution like this. So we'll talk more about this on Monday. But for this problem right here, we just need to assume this. Okay, for a sound wave. This is standard. We take this capital U to be real, not only real, but positive. This is the amplitude. And we'll take the real part here, and we just care about, the directionality is not going to be important here. So here's the particle velocity for a monofrequency sound wave of, you know, frequency omega and wave number k and speed of sound c. We have to satisfy this so-called dispersion relationship here. Omega is equal to ck. So we're going to look at Euler's equation here. Euler's equation has a nonlinearity in it. That convective, the spatial part of the convective derivative. And we're going to estimate its order of magnitude. In Euler's equation, here's the term, the nonlinear term. It's got a product of u's here. We just want to get an order of magnitude estimate. So you can see that this u grad here is going to be u times the x derivative. We're going to get this. If we substitute in what u is, we get this. Now, I just want an order of magnitude. I'm not going to worry about these sines and cosines. This has the same order of magnitude as k times u squared. All right? We want to compare this part in Euler's equation, the nonlinear term in the convective derivative, with the linear term. Here's the linear term. When I take the time derivative, I bring out an omega. So I get this. This is of order that. Okay? If we look at the ratio of these two terms, the nonlinear term to the linear term here, we just take this divided by that. We use the fact that omega is equal to ck, and we find that the ratio is the particle velocity amplitude divided by the speed of sound. That's called the acoustic Mach number. Okay? And we can see now quantitatively when we can ignore this. In linear acoustics, we ignored this, but we didn't quantify it. We just said, well, u is small in some sense. Now we have quantified it. And I promised you we would do this. It's an important thing. So in acoustics, when you have a particle velocity that's anywhere near the speed of sound, your linear theory is going to break down. Because for one reason, you can't neglect this anymore. Which is what, in linear acoustics, we tossed this. We got rid of it because it's quadratic in U. So this is one of the conditions. You know, the condensation has to be small. The acoustic pressure has to be small compared to rho naught c squared, right? Remember that? It's not the equilibrium pressure. And we have to have a relatively small acoustic Mach number. Okay, so does anybody have any questions? Okay, so any general problems? Oh, I want to tell the distance learning students, and I need to send out a message on this. When you have questions about anything, call me or send me an email message. We might be able to take care of it on the spot. If not, we can arrange a time when we can meet by a telephone conversation. Gene and I looked at Collaborate yesterday, the use of Collaborate. I'm not really crazy about that in Sakai. So I think for the time being, we're going to handle issues with the distance learning students with over the phone. Okay? So, and you guys here, you know, you can always arrange to see that you can drop.
Collaborate from
Oh.
home yesterday. It worked well from my home PC, but when I get on my NMCI during the workday, it doesn't work.
Yeah, I've heard that it doesn't work. Well, that's interesting. We've heard that we can't see your faces here because of NMCI. Is that the right initials for the security? God. Okay, thanks. He may pipe in with it. Okay. Okay, so you guys, you can always make, before or after class.
That's what keeps us from giving away all of our stuff to the enemy here. But one thing with this is Kevin Quinn from Newport. So the problem is we're on Explorer 8, and I think mid-October or early November we should be getting up to Explorer 10. So hopefully with that and the Java updates, we should be able to get up on Blackboard.
Okay, Gene understands what you're saying. I'm partially with that, but we'll keep an eye. I'll keep an eye on this. The use of collaborate. Well, we can't. I don't really want to get into it, but there are other problems that I've heard of. Okay, but we'll work this out. At least we've got live questions now, even though a little bit of a delay. Okay, thanks a lot. That's it for today.